Today we study magnetic fields. You are very well acquainted with magnets and what produces a magnetic field. Magnet, your magnet consists of two poles, north poles and south pole. North pole emits magnetic field and south pole into the south pole magnetic field comes in. Magnetic field never breaks and they are always connected such a way. Unlike the electric charge, magnetic field survives only as a dipole. For example, positive charge is a pure source, and negative charge is a sink for the electric field. Sure, north pole is the source and south pole is the sink. However, in the case of electric field, the charges are separated, so this is positive and negative. They are monopoles. So electric monopoles. However, in the case of magnetic field, magnet consists of north and south poles. They are always connected. If you break a magnet into two pieces, they become two separate magnets. Each magnet has north and south poles. So magnetic field, the generator for the magnetic field is a magnetic charge, and magnetic charge is not a monopole but dipole. That's the biggest difference between the electric field and magnetic field. Magnetic monopoles have never been confirmed. Electromagnet. Electric current generates magnetic fields. If there is a current flowing, the magnetic field is generated. Current I generates a magnet. Electromagnet. Or sometimes we can construct a coil that magnifies the magnetic field. The current is flowing. The strong magnetic field is generated inside the coil. An orbital motion of an elementary particle produces a magnetic field proportional to the orbital angular momentum. For example, a proton, electron. This is a hydrogen atom, and electron has negative charge is rotating, not exactly following this circular path, but electron makes a current. The current is the opposite direction, I. When it generates a plate, current I is flowing, then the magnetic field is generated. We shall find that some mu is called the magnetic dipole, and magnetic dipole is if there is a circular current, there is a surface A, area A, and normal vector n hat, then the magnetic dipole is current times area and proportional to the normal unit normal vector to the surface, close the surface enclosed by the orbit. An elementary particle such as an electron or proton has an intrinsic magnetic field around them because of its spin angular momentum. The motion, particles of motion, generates an orbit. The angular momentum related to this orbital motion is the orbital motion. Generates the angular momentum that is called the orbital angular moment. However, an electron, even though it is not moving, it does have a magnetic dipole that is called, we use a subscript S, spin angular momentum gives magnetic dipole. The orbital angular momentum generates a magnetic dipole. This one, mu L. Orbital angular momentum generates the magnetic field. Even though there is an orbital motion, elementary particles such as electron, proton, neutron, they have their own intrinsic magnetic dipole. That means that they have their own intrinsic angular momentum that is not related to the motion. So, thus we say that angular momentum that is different from orbital motion, we say spin angular momentum. Permanent magnet. Magnetic fields of electrons in certain materials add together to give a net magnetic field around the material. Actually, material, inside the material, they are composed of atoms, so protons and electrons are rotating around the nucleus. Some electrons are just to stay there. Globally, their direction of rotation, orbital motions are randomly distributed. Therefore, in general, material do not have magnetic property. It does not generate a net magnetic field. But once the external magnetic field is applied, many of them, not all of them, many of them are magnetized so that their magnetic dipoles are aligned. Once they are aligned and the external field, electromagnetic field is turned off, usually they return to the original random state, but in some cases they do not return. And once this property becomes permanent, we say it is a permanent magnet. Magnetic fields of electrons in certain materials add together to give a net magnetic field around the material. This is an unusual case. Magnetic field B. Under the magnetic field B, a charge, for example, we have a very big magnet N and S, and sure, they must be connected, or they are made of a series of magnets NS and S and something like that. Anyway, between the North Pole and South Pole, magnetic field is generated. Once this magnetic field exists, very important point is that a charged particle moving with velocity feels the magnetic force. This is a cross product, x-axis, y-axis, z-axis. V, B, if they are perpendicular, the magnetic force is F is along this direction if Q is a positive. If Q is negative, F is opposite to this direction. This is true even if they are not perpendicular to each other, but at least V and B has non-vanishing perpendicular component. V, B, and perpendicular component. So B per, something like that. So magnitude of the magnetic force is proportional to the charge, and V, B, sine theta, where theta is the angle between the velocity of the particle and magnetic field. The sign of the electric charge of the particle flips the direction. If it is positive, just like when we used I, J, K for the triad for the basis vector Cartesian coordinates, V, B, and force F, they generate some volume. If they make a volume, the sine theta is non-zero, then the magnetic force always survives. The magnitude of magnetic force is QVB sine. Here I wrote phi, so it's better to write phi. The magnetic force is always perpendicular to both the velocity and the magnetic field. Velocity, magnetic field. Magnetic force is always perpendicular to the velocity and magnetic field. The work done by the magnetic field can be computed like that. And magnetic force substituted in here. And dx, if the particle is moving with the velocity, the differential displacement should be v vector times dt. Substitute in here. Because the cross product is perpendicular to velocity. Because in here, therefore, this is always zero. So magnetic force does not contribute to the increment of the kinetic energy of the particle. But this is a force, so it does change the direction of the particle's motion. However, it does not change the speed. Even the velocity changes, the magnitude of the velocity, that is speed, is invariant under the magnetic field. The SI unit for the magnetic field is Tesla, and capital letter T is used for Tesla, and Tesla can be understood as the magnetic force is in here. If I replace this force with Newton and the charge Coulomb, velocity meter per second, then it becomes a Newton per ampere. Coulomb per second is ampere, meter. That is understood as the Tesla, another expression for the magnetic field unit. And 1 Tesla is 10 to the fourth Gauss, named after Gauss. Let's consider magnetic field lines. B is tangent to the magnetic field line. It is exactly the same as the electric field line. Electric field line is a continuous curve at any point tangent, represent tangent to the field line. Each field line at a point tangent is the direction of the magnetic field. Okay. So magnetic field direction is this. Tangent. The spacing of lines represent the magnitude of B. Spacing, narrow spacing. The spacing is bigger, smaller. Here, strong magnetic field. The density of field lines is proportional to the strength. Here, weak. Stronger, B is stronger where the lines are closer together. And conversely, the magnetic field lines for a bar magnet is shown in the figure. The lines all pass through the magnet. It does not break, and they all form closed loop. All of the curves are closed loop. Closed loop. Closed loop. That means they are passing this magnet, and magnet and a magnet is a dipole. Because it's dipole, loop is closed. Any magnet is a magnetic dipole. North pole emits field lines. North pole emits. This is source. This is sink. South pole is a sink, and the North pole is the source. Field lines enter the South pole. Field lines enters the South pole. Opposite poles attract each other. north-south, south-north-south. In case it is south-north, then it's fixed to rotate this axis. Then, because of the torque, it flips the direction and eventually it becomes north-south. They attract. Attractive force. Like poles attract each other. No, like poles repulse each other. This is wrong. Repel each other. If V is parallel or anti-parallel to B, then magnetic force disappears. A magnetic field exerts a force on a charged particle if the particle is moving across the field lines. If the velocity is zero, sure, magnetic field disappears. Next, we consider crossed electromagnetic fields. Thomson's experiment. This is the experiment by J.J. Thomson, who discovered the electron for the first time. Okay. Let us study crossed electromagnetic fields. Actually, the electromagnetic force on a charged particle is, first of all, on the electric field, it feels the electrostatic force, Q times electric field. And it feels the magnetic force, this is Q, V cross magnetic field. So electromagnetic force is the sum of electric force and magnetic force. Electric force is independent of velocity. It is absolutely determined by the electric field multiplied by the weighting factor charge. But magnetic force is a little bit complicated. It depends on the velocity as well as the charge and the magnetic field and the direction. And we must have some perpendicular component with respect to the magnetic field. So I mean the angle between V velocity and V is not equal to 0 or 180 degree. Okay. Here, there's a potential difference. Potential difference is applied to a filament. And filament is a heated and charged particle, actually electrons. Electrons are being emitted from the filament. As soon as electrons are emitted from the filament, inside this tube is almost a vacuum. the electrons accelerated. In order to have the electrons accelerated, we put positive charge on it, relative to here, so negative. Then the electric field accelerates the electrons because the electric field is in this direction, and QE, because the electrons are minus E, charge of an electron is minus E, electrons are accelerated. There's a small hole so that the accelerated electron goes straight to this space. In this space, there's a potential difference between here, this is positive and negative. Therefore, in the vertical direction, the electron feels the electric force, QE again. This electric force is upward. QE equals minus E electric field. In addition, there is a magnetic field that is coming into the page. So this plane is the same as this plane. Magnetic field B is entering into this cross. Cross means enter into. So coming out of the surface. So cross means the magnetic field is going into the paper. And we have QV. QV equals minus EV. So V is along this direction, minus EV is along this direction. Or magnetic field and we have V cross B. V cross B upward. Because V cross B is upward, minus E V cross B, that is Q V cross B, is downward. So here electric force is upward and magnetic force is downward. If we turn off the magnetic field, the electron will deflect to this position, E only. If we turn on the magnetic field, magnetic force attenuate the force And if magnetic force is strong enough, B strong, it will go down. And at some point, electric force and magnetic force cancel to make an equilibrium. And finally, on this screen, electron arrives at the horizontal center axis point when the two forces cancel. Let's see. A hot filament emits charged particles at the rear of the vacuated tube. Electrons emit. A potential V accelerates the electrons to V when they pass the screen C. This potential difference accelerates the electrons to let it move with the velocity V. After passing C, electrons form a narrow beam because of this small hole. We choose I to the right, J upward, K coming out of the paper. Velocity is proportional to I hat. Electric field is going down, minus J hat. Magnetic field is 0, then it deflects upward. The vertical deflection Y of the particle, this is the vertical deflection Y. Vertical deflection of Y. At the end of the cross field region is uniform acceleration with A. And this A can be computed by dividing the electric force by mass of the electron. And the time of flight, because the acceleration is along the vertical direction only, the horizontal direction has a uniform motion. Horizontal direction, it has a length L divided by initial velocity. So, substitute this one here and this one in the acceleration. We end up with the vertical deflection when magnetic field V equals 0. When magnetic field is turned on and electric field is turned off, then only the magnetic force applies. That is this. As we have already seen, the acceleration, the force, electric force is upward and magnetic force is downward. And the amount is EVB. Finally, when there is no deflection because of the cancellation of electric force and magnetic force, we have a constant equation, EE equals EVB. EE cancels and we have velocity. What is the velocity? The initial velocity when it comes to the cross field. Velocity is the electric field over magnetic field. The deflection Y due to the electric field can be used to measure the ratio. Here. When both the electric field and magnetic field survive and when they do not cancel, the Mass over charge ratio for the electron can be computed by evaluating this number, because this one is substituted in the velocity squared in the denominator. Thomson claimed these particles, the electrons, are found in all matter. He also claimed that this particle is lighter than the proton by a factor of more than 1000. Now it is known to be 1836.1526, and so on. Thomson was awarded the 1906 Nobel Prize in Physics for his work in the conduction of electricity in gases. An electron is traveling with velocity v horizontally along the direction I have. A uniform electric field is going down. If it is an electron, force is minus E electric field, so electric force is going up. The electric force, this is J. Minus E, electric field is minus EJ, therefore is EEJ hat is our word. This direction is J hat. Magnetic force is Q V cross V minus E, V equals V I B direction of B is unknown. If is minus K, IKJ, then it is IKJ minus J E V. Minus J E V B. Okay. If it is E equals E over V, then we have negative sign. Therefore, these two cancels. Charge Q moving with V. Here's the magnetic force, QV cross V. Under the same magnetic field, F QV cross V, same magnetic field, minus Q charge with minus V. They are the same, because negative, negative, positive. Next, we consider the determination of charge carrier sign. This is called the Hall effect. The Hall effect is drifting conduction electrons are also deflected the magnetic field. A strip of copper carrying a current I is going down, is immersed in a magnetic field. First, we consider the negative charge carrier. And here, positive charge carrier. Current I is flowing down. Drift velocity is going up. Again, negative charge, drift velocity is going up. Positive charge, current parallel to the drift velocity. Okay. First, magnetic field is turned on. We draw this figure. Magnetic field is B field is going into the plane. This is the plane where the right figure stands for. V. So V cross B. This direction is a V cross B. Because it is V cross B, the electric charge minus V cross B is the magnetic force on this negative charge. That is, therefore, electrons move to the right. If the electrons move to the right, the left-hand side is positively charged. The induced electric field is generated because of the accumulation of negative charge on the right and positive charge on the left. So, V left is greater than V right. In case the charge carriers are positive, then, for example, charge Q moving with V has a magnetic field, magnetic force. Charge minus Q moving with minus V has the identical force. Because the charge carriers are positive, so positive charge feels and the current is opposite, just like V and minus V and Q and minus Q. So positive charge accumulates on the right. Hence, the negative charge is accumulated on the left. Therefore, if the charge carriers are positive, then potential on the right must be higher than potential on the left. So, if we measure the potential difference between the edges, then you will determine whether the charge carriers are positively charged or negatively charged. The result is Hall potential V left is higher than the V right was really measured, and the other case was not measured for the copper string. So in 1879, Hall was a graduate student, 24-year-old graduate student at Johns Hopkins University, and he discovered this effect. So Hall effect determines the sign of the charge carrier of a conductor. Regardless of the sign of charge carriers, accumulation stops due to the induced field tending to push additional carriers to the left. The force quickly reaches equilibrium. That equilibrium condition is this. This electric field is generated by electric field is the whole potential divided by the distance d. Whole potential, V left, V right, is the whole potential, and the whole potential divided by the width V, that is the electric field, induced electric field because of the accumulation of charges, and that force, induced electric field, apply the force for an electron, and this is the magnetic drift velocity cause the magnetic force, and these two make an equilibrium. So from this we can substitute the drift velocity. Drift velocity is a current density per number density times electrons charge, and current density is current divided by the cross-sectional area, and we can substitute this drift velocity into this expression. And the electric field is the whole potential divided by the width of the strip, and drift velocity is replaced with this expression. Finally, from this relation, we can determine the number density of charge carrier inside the conductor. All right. Okay. Number 4 is the application of the previous problem. Next, we consider circulating charged particle. A charge Q with mass m and velocity v, perpendicular to the uniform magnetic field, travels along helical path. Under the magnetic field, perpendicular to this velocity, charged particle magnetic field feels a magnetic force toward the center and make a uniform circular motion. In addition, if the observer can move with respect to this circular orbit, then in general it becomes a helical motion. If you look at this motion in this direction, it is a circular motion. So in general, it is a helical. Uniform circular motion is, for the case of there is a velocity, is the velocity parallel to the magnetic field is vanishing. Anyway, the magnetic force does not work. The velocity squared is a constant as long as the electric field is vanishing. The centripetal force is the source of the circular motion. That is mv squared over r, or V equals R omega, so mR omega squared. So this is a centripetal force for the uniform circular motion. The magnetic force is QV cross B when velocity V is perpendicular to the magnetic field, then QVB equals mv squared over R. So square and single power cancel, and R equals mv over qb. Period t is 2 pi over omega, or multiply R. That is 2 pi R over V. Here the radius R is replaced with mv over qb, and vv cancel, and 2 pi m over qb will be the period. And frequency is a reciprocal of the period. Angular velocity or angular frequency is 2 pi frequency, or 2 pi over period. That is Q, this substitute in here, the QB over M. The velocity parallel to the magnetic field is invariant. If it is zero, it is uniform circular motion. If it is non-zero, it makes a helical motion. The velocity perpendicular to the magnetic field is invariant. The magnitude of the velocity. The magnitude of the velocity. Of the velocity is invariant. The direction of perpendicular velocity is oscillating. The resultant path is a helical motion. These are applications. A charged particle is accelerated, is a positive and negative. So accelerated particle must be Q becomes negative. The velocity is in here. We draw a figure. This plane, magnetic field is coming in, B. Magnetic field is V is here. V cross B is going upward. V cross B. Because charge is negative, so Q V cross B, Q is negative, is going down. Therefore, it makes a circular motion in this direction. This potential gives a kinetic energy from rest to V. So kinetic energy is the potential energy gained between the two plates. Because of this, speed of the electron, speed of the negatively charged particle when it enters into the magnetic field can be computed in this way. And after that, we can make use of the relation for this relation. that is making a uniform circular motion on the magnetic field that is perpendicular to the direction of the velocity is determined like that. Using this, we can measure the diameter or radius. If it is here, radius is proportional to the mass, square root of the mass, keeping everything the same. So we can measure the potential, electric charge, and magnetic field, and then we can measure the radius of this circular orbit to measure the mass. So we call this machine as a mass spectrograph or mass spectrometer. This is an application. Cyclotrons and synchrotrons, they are accelerator, making use of the fact that charged particle moving with the velocity perpendicular to the magnetic field is making a circular motion. There are synchrotron, a cyclotron, and synchrotron. Synchrotron, you can see this is like a D. So this is one D and this is another D. So cyclotron is composed of two Ds. So this is called the D right and D left. In either the right or the left, they are making a circular motion because the magnetic field is perpendicular to the motion. But you notice that radius of this circular motion is increasing. So initially it used to be making a circular motion if there is a uniform magnetic field. However, at the end of half of cycle, there is another acceleration by applying potential difference, electrostatic potential difference. That makes the electron or charged particle accelerate. So potential gap give rise to the kinetic energy increment. Kinetic energy is increased by the electric field. So that electric potential is generated by oscillator. When in this direction, we must accelerate. So for a negatively charged particle, minus plus. And when it passes from the right to the left, it flips the sign to minus to plus. Then electron, for example, accelerates. The radius increases. Accelerates. The radius is increased. In such a manner, circle, radius increased, circle, radius increased, the circle, radius increased, the circle, radius increased. This kind of acceleration, spiral acceleration, is synchrotron. However, if we use a synchrotron to accelerate a particle, the size must be increased arbitrarily large. So the expense is tremendously higher when we want to achieve a very high energy. So cyclotron is not, it is efficient for low energy case, but to achieve the high energy acceleration, cyclotron is not efficient. Another one is synchrotron, and read it through the synchrotron. And right now there is a world's largest synchrotron is called Large Hadron Collider. Here, R increases as we accelerate the charged particle in the cyclotron. It is impossible to build a cyclotron with infinite dimensions. Synchrotron isolates a charged particle in a circular path rather than a spiral path, that is for the cyclotron, by increasing both the V and F oscillation. Magnetic force on a current carrying wire. We learned that magnetic force is Q V cross B. Here, Q V can be delta T B. So delta Q over delta T and delta X V. And this is current, the length element of wire, a wire of length L carrying current I feels the force, that is that Q V cross B is rewritten in the form current differential length element vector cross magnetic force. A wire of L, length L, is here. Magnetic field, current I. I B. IL cross B. If I is positively charged particle, so force is upward. Torque on a current loop. For example, magnetic field is to the right. And here, this is the magnetic, and current is flowing. So in this, consider case 1. So B L 1 is in this direction. So following the current direction. L cross B. This is L1 cross B. So going up, force is going up. On the other hand, this side, opposite side, L3 is entering into the page. So this opposite direction. So L3 cross B is this direction. What about this? It's going down. So current is going down. So making some angle. To this side 2, L2 cross B. L2 cross B is in this direction. However, the other side has some force. Magnetic field is the same, but force is opposite because the direction of current is opposite. So these two forces cancel. These two forces cancels too. However, these two forces exert a torque. F1 plus F2 equals 0. Net force equals 0. However, net torque is not 0 because we have the central axis. With respect to the central axis, force is along this direction. There's radius, force. And amount of force is the same. They are opposite direction. R cross P. About this is R per. So R per F1, absolute value, that is rotating in this direction. Here, another force rotating in this direction. So these two torque adds up. F1, I L1B, L1, this length is A. L2, this side 2, this length is B. L3, the same but opposite side. L4, same but opposite side. F1, L1, and magnetic field. So I, AB. This is the width A. F2, IBB, but there is a cosine theta. However, we do not have to worry about it because this cancel for F4, we have seen this one. These F2 and F4 cancels exactly. So F1 and F3, they cancel. 2-4 cancels, but torque of 2-4 cancels too. But torque of 1-3 does not cancel. They add up. For example, we have this amount, this sign is different. You know, This is half of B vector. This is a minus half of B vector. So this is minus, this direction minus, and this is a plus. Force minus, oh, here. Force, IAB, 1, 3, IAB, same, but negative sign. Therefore, 1 plus 3, we have this amount, IAB times the magnetic field, and 1/2. And negative sign stands for the torque is along the clockwise direction. This is negative. Counterclockwise, it is positive. Along the k-axis. Finally, if we add all 4 torques, 2 and 4, each of them is vanishing, that they are 0. 1 and 3, they add up. That is minus k vector, and I, A, B, B. Here, current A times B is area. This is A, this is B, this is area, and this is magnetic field. We say magnetic field is along this direction, B. This is area of side A and B. This is the area A. Normal vector is n hat is normal to this surface, and this normal to the surface, this normal vector is making an angle theta with the magnetic field B. We notice that the normal vector, the magnetic field B, and n hat, the cross product. And cross B, and cross B is entering into the paper, and cross B is entering into the paper. But we note that K, unit vector of K, is coming out of the paper. So this one is minus of this direction. Hence, we have minus k hat, IAB B sine theta is actually IAB is current I times A. We use magnetic dipole, and my magnetic dipole vector is mu times n hat, and mu cross B B is to the right, and this one is actually the net torque. Okay? This is the magnetic dipole moment. This is I, A, and hat. This is the direction of the magnetic field, and angle theta, mu cross B, mu theta B. This direction is mu cross B. Okay? Because the angle sine theta is appearing here. So we call mu to be the magnetic dipole. Magnetic dipole moment under the magnetic field feels the torque, and the corresponding potential energy is minus mu dot B.